Okay, let's get started. So in this talk, I'll tell you about our recent results on sublinear time and space algorithms for correlation clustering. This is a joint work with my advisor Sepehr at Rutgers. So to begin with, let me motivate this problem and define what is correlation clustering. So correlation clustering has its applications in real world. So for example, if we are given n documents and each document is about some topic, okay? And each pair of documents are either similar or dissimilar. So for example, for these three documents, the first is about US election, the second one is about UEFA Champions League, which is a famous soccer tournament, and the third one is about climate change summit. Okay, so our goal is to find a clustering that puts similar documents together and dissimilar ones apart. For example, among these three documents, the first and third are more or less similar. They are about politics, and the second one is about sports. So we're going to put the first and third together, and the second one in another cluster. So the problem becomes very interesting when a document is similar to multiple documents that are mutually dissimilar. For example, we are given the first document, Barcelona and Catalan independence. So Barcelona is a soccer club that competes in UEFA Champions League, but it's also involved in some political movements. So it's similar to both the first and second documents. However, the first and second documents themselves are dissimilar. Okay. So now let me be a bit more formal to give you the formal definition for correlation clustering. So suppose we are given a labeled graph G equals V and E. As convention, V is the set of vertices and E is the set of the edges. Okay, so in fact, in correlation clustering, we deal with labeled graph, which is complete graph. So for each vertex pair, there's the edge, and each edge is labeled as either -1 or +1. For example, if I'm given this graph, so it's 5 vertices, and it's complete graph. And the edge V1, V2 is the positive edge, and edge V1, V3 is the negative edge, and so on and so forth. Okay. So in correlation clustering, one of the most well-studied goals is this disagreement cost. So what does it mean? So for the graph I've shown you, so if we implant the cluster as shown in the picture, then there are two types of costs I want to count. The first one is a pair of vertices that share a positive edge, but they are crossing different clusters. For example, this V2 and V4. You can think of them as a pair of similar documents, but they are put into different clusters. Okay. And the second type is the negative edges inside the same clusters. So for example, in this V3 and V4 edge, it's negative, but in the same cluster, then we're going to charge a cost for it. Okay. So we are going to go over all the pairs of the aforementioned kind. That is, they share a positive edge, but they're in different clusters, or they share a negative edge, but they are in the same cluster. Okay, and we are going to count all of them towards the total disagreement cost. And note that different from k-means or k-center clustering. So here we don't have a predefined number of clusters. So we can pick whatever many number of clusters we want to minimize the cost. To give you some further example, so in this example, we have V1, V2, V3, V4. And if we put V1, V2 in a cluster and V3, V4 in another cluster, then we have a cost of 0 because we only have positive edges inside clusters and negative edges cross clusters. Okay. However, if we do some goofy things instead, we put V1, V3, V4 in a cluster and V2 in a singleton, then the cost is 3. Because we're going to pay for the positive edge of V1, V2 and negative edges V1, V3 and V1, V4. Okay, so let me tell you something about the state of affairs of correlation clustering and what are our main contributions. So there are some classical results for correlation clustering. So we know that the exact solution for this problem is NP-hard. The best polynomial time algorithm achieves the 2.06 approximation by Chabla et al. So this algorithm is based on some linear programming techniques. And for combinatorial algorithms, there is this simple pivot algorithm that achieves a 3 approximation by Island et al. Okay. And here when talk about C approximation, I'm talking about to give a clustering that achieves the cost of at most C opt. And here opt is the cost of the optimal correlation clustering. Okay. So the polynomial time algorithms is not the end of the story. So in modern day applications, there's this challenge of big data. That is, for some data, like even reading or storing the entire input is prohibitively expensive. Okay. So one remedy to solve things that's polynomial time algorithm that's not able to implement is these sublinear algorithms. So these algorithms works with resources that are substantially smaller than even the input themselves. So for example, if I give you a graph, I only read part of the vertices and the edges like that are marked as red, and for other vertices and the edges, I either don't read them or I don't store them. Okay. So now there's a quest for sublinear algorithm for correlation clustering, especially for modern day massive data applications. So when talk about sublinear algorithms, there are two regimes. So I will introduce them in order. The first one is sublinear time algorithms. So when talk about sublinear time, we need some model. So the standard model for sublinear time algorithm is this agility list model. So in constant time, we can query edge and fix a vertex. In constant time, we can query one of its neighbors, or we can query its degree. Okay. And under this model, the known results for sublinear time algorithm is this local correlation clustering algorithm by Bonchi et al. So they show that within order of n over epsilon square time, we can achieve a 3-opt plus epsilon n square approximation. So note that this is different from the C approximation I talked about because there is an extra additive error term of epsilon square. Unfortunately, this epsilon square additive error seems inherent. In their paper, they show that if we are only allowed to make small of n square queries to the agility list, then there's no C opt plus epsilon square approximation for small constant C on epsilon. Okay. And in fact, in our paper, we show that if we are focusing on purely multiplicative approximation only, there's no finite C approximation if we're only allowed small of n square queries to the agility list. Okay, even like C is exponential to n or something. So I won't focus on the proof of these negative results, but I want to give you some insights that to break this quadratic barrier for multiplicative approximation, like we really need some new model. And in our result, we use this agility list for the positive subgraph instead. So what does it mean for the agility list for the positive subgraph? So we tweak a little bit. Okay, now we are allowed to query a positive edge in constant time and fix a vertex V. We're allowed to query one of the neighbors, one of its positive neighbors, on its positive degree in constant time. So to give you some more illustration, I give you the agility list for the original graph, and I color coded the positive neighbors as green and negative neighbors as red. Now I'm going to throw away all the negative neighbors and only focus on positive ones. And now for fix a vertex, we can query a positive neighbor in constant time, and then we can query the positive degree in constant time. Okay, good. So our first result is shows that given this access to the positive subgraph G+, there exists a sublinear time algorithm that with high probability finds a constant approximation for correlation clustering with order of n log square in time. Okay, compared to the omega n square lower bound, this is almost quadratic improvement. So now let's change the context a little bit and talk about sublinear space algorithms. So we studied these algorithms under the framework of insertion-only graph 3D model. So under this model, we are giving the vertices in the beginning, but the edges arrives one after another in the stream. So for example, if you give these 5 vertices, and when t equals 0, there are only vertices. When t equals 1, this positive edge v4, v5 comes, and t equals 2, the negative edge v1, v4 comes, and so on and so forth. Okay. So an ideal algorithm, a streaming algorithm works within only a single pass, and it does not necessarily store all the edges. So indeed, actually, the algorithm are interesting when its memory is small of n squared, because otherwise it can store everything and run the best offline algorithm. And the dreamland scenario is the memory of order of n polylog n, which is called semi-string memory. So why this is good? Because actually in many applications, this is the necessary memory to even output the answer themselves. Okay. For example, in correlation clustering, we need polylog n bits to encode the cluster for each vertex, and there are n of them. Okay, good. So under this semi-streaming memory constraint, by the way, it can also be shorthanded as noted as O tilde of n, which has used this notation throughout the talk. So there are some known results with this memory. So in this ICML 15th paper, An et al. Showed that there's a 3 approximation with order of log n passes. And in a very recent paper by Cohen and et al. In last year's ICML, they show that there is a constant approximation with 6 passes. But before our work, there's no known results with a single pass. So our results basically settles this problem. We give a sublinear space single pass streaming algorithm that with high probability finds a constant approximation for correlation clustering and use a memory of order of n log n edges. Okay, this is almost optimal. So in the rest of the talk, I'll give you some intuition how our algorithm works. But before that, let's do a review a little bit and see the main challenge for designing correlation clustering algorithm in the sublinear regime. So earlier sublinear algorithms for correlation clustering mostly simulates the pivot algorithm. So the pivot algorithm is extremely elegant and easy to implement, and it essentially computes a random order maximal independent set on the positive subgraph. Okay. However, to compute the maximal independent set, there are some barriers. So we know that under the identity list model, there's omega n squared time lower bound. And similarly, under a single pass over the stream, there's omega n squared space lower bound. Okay. So in the recent paper by Cohen and et al., they actually achieved constant approximation in 6 passes with a new idea. So without diving into the detail of their algorithm, so the high-level idea of their algorithm is to cluster different vertices based on the density of their edge connectivity. Okay. So in particular, for a graph as shown in the picture, let's see there is a 5-click here, almost 5-click here, and 2 standalone vertices. It will put the almost clicks in the clusters and the standalone vertices into singletons. Okay, so why this is good? So just to give some intuition, so if we focus on this positive edge that is going to paid by this kind of clustering, and so if the optimal clustering also splits them, then we're going to, there's no extra cost. So suppose the optimal clustering actually put them together. Okay, so I'm going to show you that the optimal clustering has to pay a lot of cost. So why? Because so consider a vertex that is not inside this same cluster that has a positive edge connecting to this to this right-hand side right vertex, and then we are going to pay for this positive edge. And on the other hand, consider a vertex, light blue vertex that is inside this cluster. So it has a positive edge to this vertex, but it has a negative edge towards this right-hand side red vertex. So we're going to pay for the negative edge. So in this way, even if the optimal clustering put these 2 vertices together, the optimal clustering is going to pay a lot of cost, and our algorithm should be competitive against it. Okay, so that in this way, they show that they can achieve a constant approximation. So now let's step back a little bit. So if we look at this clustering result, we will find that the algorithm put these densely connected components together, okay, these densely connected vertices together, and standalone vertices apart, okay? In other words, their algorithm implicitly divides the graph into 2 types of vertices. The first one are densely connected components, and the second type of vertices with sparse edge connections, and they implemented this with 6 passes, So now our observation is that is this kind of decomposition first of its kind? So the answer is no. There is this kind of powerful tools called graph-dense, sparse-dense decomposition from the graph streaming literature. The line of work actually initiated from the graph theory context and more recently in the distributed and streaming graph coloring. Okay, so now let me tell you a little bit about what is sparse-dense decomposition and why it helps correlation clustering. So a sparse-dense decomposition, roughly speaking, categorize the vertices into two types. The first one is the almost cliques, which are the vertices that are densely connected with each other, and their degrees are around the maximum degree delta. And for the vertices that cannot join any almost clique, we call them sparse vertices. So a natural idea here is to decompose the graph on the positive subgraph G+, and then do the correlation clustering based on the results. So why this is good? So let's look at it from this example. So in this example, the maximum degree is 4, okay? And it has like, this is this is a 4 click, this is a 4 click, and this is almost 4 click, okay? So based on the rule for sparse-dense decomposition, they will put the red vertices into almost clicks and light blue vertices into sparse vertices. So now what we can do? We can put each almost click as a cluster and each sparse vertex as a singleton cluster. Okay, so why this is good? So remember, this is a positive subgraph. So for each almost click, there are a very small number of non-edges inside each almost click, and there are a very small number of edges outside. So the cost is small. For the low degree sparse vertex, there are not many edges on it, positive edges on it, so the cost is small if we put it a singleton. And the interesting case is this kind of light blue high degree sparse vertices. So it has many positive edges, but it also has many non-edges, which translates to negative edges in a complete graph. So whatever we do, even the optimal cluster has to pay a lot of cost for it. So if we put it a singleton, it won't be too bad for the correlation clustering cost. Okay, so this is actually the main takeaway of this talk. So how sparse-dense decomposition helps correlation clustering. But this is not the end of the story. Now there are some major problems for canonical graph sparse-dense decomposition. And one of the problem is it only works with the maximum degree delta. But this is bad for correlation clustering. So why? Think about this graph, which has 2 big clicks and 1 small click. And now, because canonical sparse-dense decomposition works with the maximum degree delta, so it will put these big clicks as almost clicks, but every vertex inside the small click as a sparse vertex. And now if we do the same thing, we put almost clicks in a cluster and each sparse vertex as a singleton. So suppose this small click is of size root n, we will induce a cost of n, okay? But optimal cost is 0. So this is bad. So one candidate to remedy the issue is the local sparse-dense decomposition by Alon Assadi. So a local sparse-dense decomposition means that the almost clicks is now dependent on a local maximum degree. For example, there's a 3 click here, almost 5 click here, and both of them will be identified as almost clicks based on their local maximum degree. Okay. So however, that version doesn't work for our purpose either. So there are some problems with their guarantees for the neighborhood of sparse vertices, and more importantly, their work emphasized on the existence of such decomposition, and it is not clear if we can do it efficiently. Okay, so to get a sparse-dense decomposition for correlation clustering, so we actually propose a new type of sparse-dense decomposition. So the guiding principle here is that for each almost click, okay, we have this local almost clicks. So for each vertex v in an almost click k, it has a very small number of non-edges inside k and a very small edges outside k. And its size is around the degree of v for each vertex inside. To put it more concretely, so in this picture, if v is inside ki, and let delta ki be the max degree in ki. Okay, for each vertex v, it has at most epsilon dot k non-neighbors inside ki, and at most epsilon dot k neighbors outside ki, and the size of ki is around delta ki. Okay, this is our new definition for almost cliques. And we, as in correspondence, we also have this new notion for local sparse vertices, and the vertex v is said to be sparse. It has if it has a subset of neighbors SV, such that one, this subset has to be large, it has to be a constant fraction of its neighborhood. And second, for each vertex u in SV, the difference of the neighborhood between u and v is large. And different neighborhood is defined as the vertices that are in the neighborhood of u, but not in the neighborhood of v, plus the neighborhood of vertices v, but not in the neighborhood of u. Okay? So to put in the picture, if v is a sparse vertex, then it has a large fraction of its neighbors as v, such that for each vertex u inside, and that the neighborhood between nu and nv is different. So the difference between the neighborhood is large. Okay. So now, why this new decomposition is good for correlation clustering? So well, I'm going to show you the algorithm for it. So now, after doing the correlation, after doing the sparse-dense decomposition, we can do the old scheme I've already shown you. So we can put each almost clique into a cluster, and for each sparse vertex, we create a singleton. Okay. So in the flowchart, the algorithm will just be as the following. So the first thing I want to show is this is good for correlation clustering. So note that there are three types of costs induced by our clustering scheme: the positive edges on the sparse vertices, the positive edges between different almost cliques, and the negative edges inside each almost clique. So now, in the same spirit of the Cohen et al. Paper, so we can actually show that the sparse vertices incurs at most a constant to the optimal times of optimal clustering cost. And similarly, the positive edges between different almost cliques incurs at most a constant times the optimal cost. On the other hand, the negative edges inside each almost clique incurs at most optimal cost. So in summary, we get the order of one approximation. Okay. Now let me tell you a little bit about why this is efficient algorithm. So note that conditioning on we have the decomposition. Now we can do this. We can assign clusters in order of n time and memory. We can just go over the vertices, look at its labels for in this sparse-dense decomposition, and then assign to the corresponding clusters. Okay. So we can write order of n time and space here. And now, how much time and space we need to find the sparse-dense decomposition? So the good news is that by our definition, we can actually efficiently find this sparse-dense decomposition in sublinear time and space. So in our paper, we show that if you are given the following information: one is the degree of the vertices, two is a random order of log n neighbors for each vertex, and the third information is the neighborhood, the whole neighborhood information for a subset of vertices. And these subset of vertices are sampled with probability around order of log n over degree of v, okay, for each v. And then if we give the three type of information, then we can compute a sparse-dense decomposition in order of n log square n time. Okay. So now we can write a order of n log square n time and order of n log n space for fun to compute this sparse-dense decomposition. And now the only thing left is to obtain the required samples for this decomposition. And we show that given the agility list for the positive subgraphs, this can be done in order of n log n time. And with a single pass over the stream, this can be done with order of n log n edge memory. Okay, so we can write O tilde n here. And then we can sum up these results as the flowchart has shown us. So with the agility of positive subgraph, we can obtain the required samples in order of n log n time. And then in a single pass over the stream, we can do this in order of n log n memory, spend order of n log square n time to recover the decomposition, and order of n time and memory for the clustering scheme. Okay, good. So let me conclude by adding some remarks. The first remark is the right model for sublinear time algorithm. So we know that under the standard agencies list model, there's no finite multiplic approximation. And under the G plus model, we have a constant approximation. So is G plus the right model? So more or less, we can say this is yes, because we also give a lower bound for if we are given the negative subgraph G minus instead. Still, with the small of n square queries, we cannot achieve any finite multiplicative approximation. Okay, so the G plus will be the most natural one for us to work on. And the other comment is about our streaming algorithm. So we introduce our streaming algorithm under the insertion only graph stream. So we note that it can be adapted to a dynamic graph stream algorithm that can handle both insertion and deletion with polylog space overhead. And the reason is quite natural, is because our sparse-dense decomposition only requires samples. And if you are familiar with the literature, this can definitely be done by this celebrated L0 sampler. So in summary, we studied sublinear time and space algorithm for correlation clustering in this paper. Okay, we proposed the first sublinear time algorithm that finds a constant approximation for correlation clustering with order of n log square in time, given the agency list for the positive subgraph G plus. Furthermore, we designed the first sublinear space single path streaming algorithm that finds a constant approximation for correlation clustering with order of n log n space. And we note that both of our algorithms are randomized. So there are some open problems. So one is right now our constant is quite large. It's 10 to the 5th to 10 to the 6th. So can we get a small constant for that? And we believe that our algorithm works much better than the worst case approximation factor on real world graphs. So we will leave the empirical study as a future direction. And also another interesting problem is to test the values for correlation clustering. In particular, if you are only allowed polylog n space, now we are not asked to output the clustering, but only output the value of the clustering. What can we do for this? Okay, so that's it. And there are some references, and thank you.